Congratulations. You made it to the end of the term. It is crazy. It's crazy. So, at the very bottom of our Moodle page for today, we're going to do the final exam review overview. It's more of an overview. And then we'll do some probability practice problems, which I handed out. And they, if you want the PDF, are posted at the very bottom there. And so it looks like this. And so that's what we'll be working through. I should open it in Notability so that we have it. Okay, good. I have this vague memory. I added stuff, didn't I?
You added the 8.5.
That's right. I knew it because I ran out of time. Do you remember where we?
You put it at the bottom.
And that's the only one that I tucked in afterwards. Okay.
Maybe even the 8.9.
Yeah, right? Maybe.
I think that one too.
Okay. Yeah, so if you haven't had a chance to look at those, you can look at those. But we'll have more practice, or some more practice with these concepts today. So I can look through them, but hopefully my solutions are kind of self-explanatory. So what I want to do today is remind you of all the things that we've learned, covered, talked about, endured, and also how many marks to expect from each section on the final exam. And so over here on the side, I'll do approximate marks because I'm allowed to change my mind a little bit, but in general, kind of broad strokes. So linear equations, things where we learned how to graph a linear equation, which we then used in chapter 3 as well for our linear programming, right? And so we graphed linear equations, we found the slope of a line, and then we used the slope to find the equation of a line. We solved linear systems, right? And so if we have two lines, where do they intersect? And then, of course, do application problems using linear equations. So those were those word problems where you had to create lines. Right. Now these, there's a kind of a lot of ground laying material here. And so there's roughly 24 marks from chapter 1. I might pare that down a little bit because I feel like that's quite hefty. But on the plus side, you've had a lot of practice with it. And so it's kind of nice to have it be weighted so high. But for comparison, for the linear programming, right? And so linear programming where you have to maximize or minimize a function. Yeah, question?
I will show you guys anyway.
Oh, after, please. Yeah. And so, what was I saying? Maximize or minimize an objective function, which we did on test 1, of course. And so I'll give you the constraints. You don't have to read them and find them. I'll give them to you just like on test 1. And so that'll be 8 marks. Oh. Then we did logic, which is not in the textbook, but it is in the notes. And we talked about the conjunction, the disjunction, and the negation of propositions. Talked about conditional statements. the converse, the contrapositive, and the inverse of a conditional statement. Now, these are on your formula sheet, right? And so, and then the biconditional, going back and forth, truth tables, which if you kind of keep your head on straight, then they're pretty fun, right? And then we talked about tautologies and contradictions and equivalences and implications, right? And those would be from the truth table, right? You would use a truth table to solve those. Now, there's more than I have paper copies. You want me to go make a photocopy? I only have the one. I'll go make a photocopy. Let me just pause this recording here. I'll let you try. I'll give you a task. Well, before I do that, let me go here. So in this booklet that I gave you, you can start while I run downstairs and photocopy. You can start working through those problems. You're welcome to work together. It's supposed to be fun. Probability questions. And then we'll work through those together. So I will be right back. Resume. All right, we're back. Logic. That's what we were talking about, right? And so the tautology and contradiction and the equivalence and the implication, those are all from the truth tables, right? So there's kind of a lot riding on the truth table. And of course, I will make you do a truth table, and it can be up to and including, I'll be clear, and including 3 propositions, right? Which is that big version, right? 8 lines. But you had one on test 1, and it'll be 8 marks from logic, roughly. That was all on test number 1. So you can see test number 1, which you got back, right? You can do the practice test again, make sure that they look kind of similar to you, right? With practice, you'll see that they're quite similar, right? And then I will post a practice final, which isn't made yet, quite yet. But I'll send out a message when it's ready. Chapter 6, we did financial math. Financial math is kind of a heavy hitter, and there are 16 marks from financial math. Now it continues on the next page. Okay. What did we do? We talked about simple interest problems, right? We found the amount of interest, the present value, discounts and proceeds. We solved compound interest problems, right? We worked on annuities, right? Regular payments and sinking funds, right? We did the present value of an annuity and an installment plan or payment, right? Finding the payment amount. And then how do you find the outstanding balance partway through the term of the loan, right? Then you have to bring that amount back that you were going to pay, and then your payment numbers become the number of remaining payments. Several stages of savings and or annuities, like the one on the test where you had to, I can't remember who it was, Mrs. Garcia maybe, I feel like it was one of those. Right? She's saving until a point, and then she wants to withdraw. Right? And then the amortization schedule for a loan, right, where you have to articulate what each payment is, how much is paying off your interest, and how much is paying off your debt, and then what's your balance, and fill in a bit of a table, just like you did on test 2. Sets and counting. Sounds easy. And maybe now that we've done it, it kind of is, but there's some curveballs, I think. But sets and counting will be roughly 20 marks. We covered a lot of ground here, right? So set notation, we talked about unions, intersections, and the complement of sets, using Venn diagrams to solve counting problems, right? Saw that on test 2. Use trees to count possible outcomes in a multi-step process. The multiplication axiom to count possible outcomes in a multi-step process. Those are the slots, right? Using the slots to solve the problems, which I find you can use the slots for a lot of these problems, right? The number of possible permutations, which is an ordered arrangement of n items taken r at a time. Just to clarify, that's NPR. And then count the number of possible permutations when there are conditions imposed on the arrangements, right? Things like it has to end in a vowel, right? Or license plates can't start with zeros, things like that, right? Factorials, right? Exclamation mark, n factorial, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Count the number of possible permutations of items arranged in a circle. Saw that on test 2. Right? It's where you have to kind of pick a point, right? Pick someone, force them to be the starting one, and then go around, right? And count the number of possible permutations when there are repeated items, right? And so we saw that, I can't remember what the word was. Did I use mathematics, I think, on the test?
Yeah.
Right, and so mathematics, there's 2 A's, there's 2 M's, right? So then you have repeated items, and so how many possible permutations are there? Count the number of combinations of R out of N items, so that's NCR. And then use factorials to perform calculations involving combinations. And maybe I should add or permutations. Right. That's like on the test where I got you to use the formula and show all the work that you do by hand if you weren't to use your calculator. And that was all kind of recently on test number 2. Which leaves us with only chapter 8 for new stuff, which I'm pretty pleased with myself. I snuck onto 1 page, or I guess 2 pages. Little wins, you know. We're looking at, what do I have here? Roughly 20 marks for probability. So for the new stuff that you haven't been tested on. And so that's what I want to do some practice with today, just so that we can go through some of these problems together. Including writing sample spaces, calculate probabilities, by examining events in sample spaces, right? The union, the intersection, and the complement of a set, of a set. I guess. But also of probabilities, I should say. Mutually exclusive events, meaning they can't happen together. The addition rule for the union of events. Tree diagrams to calculate probabilities. And we've got a practice one for today. Use combinations to calculate probabilities. Conditional probabilities, right? If you are given some information, right, you know that you have drawn 2 kings out of a deck of cards, and I will say, I promise no card problems. It's just nice to think about because we can kind of imagine, right? If I've drawn two kings already, then that affects the probability of drawing another king, right? And so that's our conditional probability. Right? But I promise, no card problems. Independent events, what we talked about last day. What you want to check there is the probability of A and B. Is it equal to the probability of A, the probability of A times the probability of B? If it is, they are independent, A and B. If they are not, then they are not independent. Yeah. And then identify whether 2 events are independent or dependent, kind of circling back to using this formula to check. And we've got some practice on that today. Then the end. Sort of. Good job. You did it. You did it. All right. Any questions about the breakdown? No? How about some probability questions? So since you all have them, I encourage you to work in groups because it might be more fun to talk it out. But I'll give you a little bit of time to, I guess, or did you finish question 1 already?
Absolutely. I wrote some things down, but I got stumped.
How about I'll pause the recording, give you some time to work through it, and then we'll go through it together. And then we'll do that for each of the questions. I'll pause it here because otherwise, wow, what a boring video. Let's go through this one. Can't tell if it's back to record. Okay, it's kind of blinking. Yeah, okay. Good. Yeah, this is what tripped me up. I didn't pay attention and I thought, oh, it wants the probability for sure. But if we just want to know how many committees, I guess I should read it for posterity. A robotics team needs to select a committee of 6 members. The team consists of 12 students from grade 8, 15 students from grade 9, and 11 students from grade 10, which means that we have a total number of students. We have 12 and 15 and 11, putting me at 38 total. So from 38, there are no restrictions. I want to choose 6. So 38, choose 6. Which if you use your calculator, which I would encourage you to do, you only have to use the formula if it says use the formula and show your work. So just use your calculator. And I should use up all the space, I guess. I should just blow it up. 2760681. Right, so make sure that when you try it on your calculator, then you get that same answer. Oh, I thought it was a question for me. It was a high five. I'll blow it up so that that's it. All that space to throw you off.
Go.
I know, it's nice and lofty. Okay. Now with some restrictions, right, which is how the final exam will go as well. How many different committees includes 2 students from grade 8, 2 students from grade 9, and 2 students from grade 10? And again, it just wants how many. And so now I want 2 students from grade 8, and I have 12 students to choose from, right? And so I want to have 12 choose 2. And whenever you're saying and, you're multiplying, right? And 2 students from grade 9. Grade 9, we have 15. And I want 2 of those. Doesn't matter which 2. And from grade 10, where I have 11, I need another 2. Let's see here. 12 choose 2. I got 66 times 105 times 55. Hopefully that's correct. I kind of whipped it together, so once I multiply that out, I get 381150. Blow that up. How many different committees include at least 1 student from grade 8? Huh. This is a pickle, isn't it? It could be a lot of work, right? Because you could have, right, at least 1 student, that's 1 from grade 8, or 2, or 3, or 4, or 5, or all 6, right? Whenever you're saying or, you'd have to or add all those probability, or add all those outcomes, which you can turn into probabilities. I keep saying probabilities, but it works the same way. So, as a little trick, when you see at least, I tend to gravitate towards using the complement, right? Because at least 1 student from grade 8, so at least 1 grade 8 is the same as the total minus none from grade 8. Better? Huh? No. Nope. If you remove the grade 8s from the total possibilities was 38 choose 6. And then if I subtract all the grade 8s from that 38, and how many grade 8s did I have? I have 12. So then I have 26 who are not in grade 8. So this is grade 9 and 10. I'm forcing them to be from grade 9 or 10. And I want to choose 6 from there. 26 choose 6. Once I use my calculator, I got 27,606.81 from earlier minus 23,0230, putting me at 25,30451. if you wanted these to be probabilities, all you would have to do, right, is just divide by the total number of possible outcomes. And then all of a sudden you would have the probabilities. Notice that once you split this up, this would become 1 minus 26 choose 6 over 38 choose 6, which is what we're more used to working with now that we've kind of graduated. This is a little bit of a throwback. I'll remove that because it would be confusing. But... Nice. Good. So whenever you see at least, it's probably going to be a little bit better, right, to do the complement, right, where you take the total and then you subtract what you don't want, right? You'd find the same answer if you did 1 or 2 or 3 or 4 or 5 or 6, but it would be a lot more math. Nice. I feel like we should do or you could do 1 grade 8. I'm spelling it out because otherwise it'll be too many numbers and it gets kind of weird. But so 1 grade 8 is going to be from 12. From 12, choose 1 times from 26, choose 5. Right, that's where you get the other 5 from. Or 2 grade 8s, or 3, and then so you'd have to do it for all of them. So or, which is plus 2 grade 8s. So 12, choose 2 times 26, choose 4. Or 3 or 4 or 5 or 6. And then you'd have to add all those up. I don't even want to write that all out. Right? You can do that. That's going to work, right? I would think of that as the brute force method, right? It's going to work. It's just going to be annoying, right? Whereas if you recognize the at least and then you say, oh, what if I just take away whatever I don't want, right? Then it's a little bit quicker. Okay. So, any questions about that one? A jar contains 12 yellow, 15 purple, and 9 orange beads. You randomly select 4 beads without replacement. Give you some time to work on it, but these will be similar to what we just did. I'll give it a pause and let be a real bummer if we ran out of time. Because I do want to spend quite a bit of time on the last question, which I probably should have put first if I want to spend time on it, because we haven't seen one exactly like it in class yet. So I want to prepare you so you're ready. It's a cute little tree diagram. All right. We've got 12 yellow, 15 purple, and 9 orange, and we want to know in how many ways can you select exactly 2 purple beads and 2 beads of different colors, which is to say 1 yellow and 1 orange, right? And so it sounds all vague here, 2 beads of different colors, but if we have to force them to be different colors, then it's just one of each, right? And so this, to me, feels exactly like what we were doing before, right? 12, choose, so for the yellows, I want 1. And from the purples, I want to choose 2. And from the orange, 9, choose 1. I get 105 and oops, I did them in a different order, I guess. Sorry. 12 times 105 times 9. I get 11340. I will make a note here that we can write, and we did see it just briefly, but to match your formula sheet, I just want to use the 12 choose 1 notation, but we could write 12, oops, sorry. 12 choose 2 like this, which tends to be a little bit cleaner looking, right? A little bit quicker to write. Just make sure you don't put a bar between here, right? Because then that becomes a fraction and that's not what you want, right? This is just 12 choose 2, right? So it's just different notation. You're welcome to use it. I'm really struggling to use this one, but I want to match what we were doing in the textbook. So I find this is a little bit nicer. And now I can't. Was I using this? Was I being sloppy? No, we were using this, right? Pretty sure. So I'm sticking with it, even though, especially when we're multiplying all these together, it kind of looks nicer, but they do the same thing. So if you prefer this notation, totally fine, but I'm gonna stick with this one. Okay. Now we want the probability that all 4 beads selected are the same color. Okay. So that means that I have either 4 yellow or 4 purple or 4 orange, right? So whenever you're saying or, you're adding those events up, right? And so I want 12 choose 4, right? 12 yellow or makes addition. 15 choose 4 or 9 choose 4. Right. Good. For the probability, right, I need to divide by the total possible outcomes. Right? Now, how many do I have in total? I have 12 and 15 and 9, which puts me at, I have 36 total. But looks good. So the total number of possible ways from 36 that I could choose 4, that's going to be the total number of outcomes. And that's the only change, like I pointed out, for the probability versus just how many ways can this happen. It's funny because once you learn the probability, then that's kind of what that's going to be your go-to, right? And so, but I think the idea is that in how many ways is supposed to be a little bit easier, but not when we're used to doing the probability. So 12 choose 4, I get 495, and then 5 choose 4, I get 1365, and then 126 divided by 58905. which puts me at 1986 over 58905, or roughly 0.0337153043. I want to see this for sure. You can skip from here. I would consider it a leap, but you could go from here to here. And that's okay. It's always nice to give me some sort of kind of stopping point, right? Otherwise, it's hard for me to give part marks if this jump is not correct. Right? If you tell me, oh, okay, I did this and I got this, and then only one of them is wrong, right? That's clearly just a little slip up on a calculator. Versus if they're all wrong, then I know you don't have the skill, right? Which is a bigger problem. And so it's hard for me. It's hard for me when you don't show all your work. It's easier to give part marks if you show more. So how's that for a non-answer?
I feel like you said it like this.
Yeah, at your own risk, I guess. But you could go from here. I need to see this, right? This idea. And of course, I want to see a probability. Now, what I am looking for, I would be fine with you just leaving it as a fraction, right? You don't have to give a decimal, right? But a lot of people are more comfortable with decimals. And so usually it ends up being a decimal. But it's
whether it's in between 0 and 1, because right now looking at the 19.
You stole the words out of my mouth. Exactly. Probabilities have to be between 0 and 1. And so then decimals are a nice way to check that. So proud. So proud. What's the probability that your selection contains beads of at least 3 different colors? Now, this at least is a little bit different because when you think about, okay, kind of map out the problem, at least 3 different colors. Well, I only have 3 different colors. And so now what that means is I need at least one of each. And my other options include another yellow or another purple or another orange. I was going to say another 9. Another orange. It's late. And so really, at least 3 different colors. There are 3 different possibilities, right? And so I could have 2 purple. Or I could have 2 yellow. Or I could have 2 orange. So when you're saying or, then you're adding, right? How do I get 2 purples? Well, I get from 15, I have to choose 2. And I need at least 3 different colors, which means I have to force the other 2, right? One of each. Right? Otherwise, I won't have the 3 different colors. And so I need to force 12 choose 1 and 9 choose 1. And when you're saying and, you're multiplying. Yeah. So I get 11, 3, 4, 0 for that one. Or 2 yellows. Means I only pick 1 purple. 12 choose 2 and 9 choose 1. I have 8, 9, 1, 0 down. Hopefully that's right. This is where the spacing got a little bad, didn't it? 2 orange means 15 choose 1 for 1 purple, 12 choose 1 for yellow, and 9 choose 2 for 2 orange, 64.80. Which means that in total here, if I add these all up, I get 26730. And I guess I'm gonna have to make this smaller because I need more room. Oops. So the probability is 26730 divided by however many ways I can choose 4 from what's my total? 36. Which is that 58905. And if I bump this over, or I ran out of room, so I actually stopped after some decimal places. 0.45378 dot dot dot. Let me check that one. I can do better than that. Two six seven three zero divided by 58905. Is it 9? Pretty bad when I'm second guessing my own writing. There. 815126. There, I'll stop there. Oh. Suppose you draw 4 beads and get no yellow beads. What's the probability that exactly 2 of them are purple? Huh? So now you know that there are no yellow beads, and so that reduces it to 24. I have, right? No yellows. I have 15 and 9, putting me at 24 remaining. And you want to know what's the probability that exactly 2 of them are purple? Well, if there are no yellows, then 2 are purple, which forces 2 of them to be orange, right? Because exactly 2 of them are purple. And so from the purples, 15, I choose 2. And that also forces from the orange, I choose 2. Divided by 24, choose 4. I get 105 times 36 divided by 10626. As a fraction, 3780 divided by 10626. As a decimal. So you can make sure it's between 0 and 1, 0.35573122253. Nice. Also, how am I doing? Okay. Any questions about that one? Kind of similar to the first one. Right? A little bit extra practice. Throwing in some probabilities. Right? For this one, I'm going to give you 5 minutes. 5 minutes, mostly because a lot of these you can just read from the table if you wanted to. All right? And then we'll go through it. But I'll pause this here. So it's risky business going back and forth. I'm going to solve this just by reading the table, which is totally fine for you to do on the final exam. But I don't want to do it together. But before I post the notes for tonight, I'll solve it with the formulas so that you can see both of them, right? But you can use either method on the exam, right? Just pick whichever one you like. I suspect that you'll like just reading the table the best. But you can do it by using the formulas, but it's a little bit harder. It's a little bit more tedious. Okay, and because I can, I'm going to make a copy and highlight it in each section. Paste it, paste it, paste it, paste it, and not for that last one. So researchers surveyed 540 students who participate in either band or choir at a university. That's a lot of people in band or choir at a university. Must be a big university. And asked whether they can read music. Right? And the results are summarized in the table below. And so we've got whether they're in band or choir, if they can read music or if they cannot read music. Right? And then we've got our total of 540 and the totals in the margins. What is the probability that a randomly selected student participates in band? Okay. And so what you're looking at here is just if they are in band, right? And so that doesn't matter. We don't care if they can read the music or can't read the music. The total is 285 out of 540. And that's the answer. Wow. Nice. Bink. You can convert that to a decimal if you want, right? But I'm happy with just the fraction. In this case, I think the fraction's a little bit nicer, right? Because it maps to the table. Right? But you can use a decimal if you want, or give a decimal, I guess. What's the probability that a randomly selected student participates in band and can read music? Right? And so I'm looking at they have to be in band and they have to read music. Okay. And the only overlap here is this 210. Okay. Question is, out of 540, right? Because it's out of the total. And otherwise, you're making it conditional on something, so it has to be out of the 540. Okay. What's the probability that a randomly selected student participates in band or, okay, that's a big one, cannot read music? So they can be in band or they cannot read music. And so inside here, you want to pick out all the highlighted ones. Then there's a couple of different ways that you could do it, right? You could take the totals, 285 and 165, and then subtract the overlap, 75. Right? And so option 1 is you could take your 285 and 165 and then subtract the 75 overlap. That's fine. Out of 540. Or option 2 is you can take the individual counts, not the totals, that you've highlighted and add those up, and what you'll find is that it's the same answer. Right? And so you could take 210 and 75 plus 90 out of 540, and hopefully either way you get the same answer. 210 and 75 and 90. I get 375 out of 540. Which, and I have this one written down as 375. One of those will do. Because you get the same answer. What's the probability that a student participates in choir given, given that they cannot read music? So now we know that they cannot read music, right? Which reduces our total to out of those who cannot read music. Right? And so we know they're in this column. And we want to know what's the probability that they are in choir. That's these guys. So it would be 90 over 165. That's the conditional probability. Are activity and music reading ability independent events? Justify your answer mathematically. There's a couple of different ways that we could solve this, but the one I want you to focus on is the generic one on your formula sheet. The test for independence. Now there's a little bit of a leap here that you have to make. Because the activity is whether they're in band or choir, and music reading ability is whether they can read music or they can't. Okay? Now the thing is, if one of these combinations are not independent, then that means the rest are also not independent, right? And so you just need to show one of the cases, and if one case is independent, then the remainder of the table has to be independent. Okay? And so what we're going to do is let's call this B and let's call this R for they can read music, because otherwise it's C and C, and that doesn't really make sense. Oh, and cute. Then it can be R and B. So, the test for independence, if the probability of R and B, right, for my pun, is the same as the probability of R times the probability of B, right? Probability of R and B, is it equal to the probability of R times the probability of B? Which means I need all three of those probabilities, but I have those from the table. The probability of they can read music and they are in band, that's 210 out of 540. Is it equal to the probability of R, which is what they can read music, which is 375 over 540, times the probability that they're in band, which is 285 over 540. $375 over 540 times 285 divided by 540. I get, on the right-hand side, I get 0.36651234557. Now remember, you want to keep a lot of decimal places here because they in order to say they're independent, they have to be exactly the same. All right, so you don't want to be doing any rounding because then they might not be exactly the same. Compared to 210 over 540, I get 0.3888 repeating, which is not the same, of course. Oh. Which means that if band and whether they can and that they can read music are not independent, right? Then that means that the whole table is not independent, right? There's dependency. And so this means the two events, I'll say, must be dependent. Or if you prefer, not independent. Independent. That's fine too. So for this one, even though it's generic sounding, right, we can just pick any combination. And if we find that they become the same, then what you would find is that all individual combinations would be independent, because otherwise there's no, that it has to be independent across the board for it to be, for one of them to be independent. Slight leap, but now you've seen it. Okay. How am I doing for time? Any questions about that one? So before I post the notes, I will solve it with the formulas, although some of them I feel like are so quick, like the first one. It's really just the part C and D that would be new, I guess, with the formulas. I'll read this one, give you just a little bit of time to map out the tree diagram and try it, and then we'll go through it together. Like I said, I should have moved this one to the front. A delivery company ships packages using 3 methods: ground, express, and priority. Of all packages shipped, 58% are sent by ground and 29% by express, and the rest by priority. Those are probabilities now. About 92% of ground shipments arrive on time. 85% of express shipments arrive on time, and 98% of priority shipments arrive on time. And then I'm giving you the notation to use. We're going to let T, capital T, represent the event that a package arrives on time, and L represent the event that it arrives late. I want you to draw a tree diagram showing all shipping methods and the probabilities of arriving on time or late. Then, what's the probability that a package is shipped by express and arrives late? You'll use the tree diagram to answer the rest of the questions, right? What's the probability that a randomly selected package arrives on time? Right? Now notice that this is regardless of how it was sent. Right? Given that a package arrived on time, what's the probability that it's shipped by priority? So I'll give you just a little bit of time. I know you need a lot of time, but I need a lot of time to go through it. So 4 or 5 minutes, and then we'll jump in. Zoom. All right. So I went ahead and I mapped out the tree so you don't have to watch me do it. But I do want to talk about why I mapped it out the way that I did. Right? And so right? Because it might be hard to choose. Okay, so if it's shipping on time or if it's arriving late, right? Or I guess arriving on time or arriving late, it might be tempting to put those as your initial branches, right? And then do the ground express or priority after that. But the reason you want to do the ground express priority first is because of all the packages shipped, which are kind of, we start up here at the top, right? Then 58% are by ground, 29 by express, and then the remainder, which would be 1 minus these two guys, which puts me at 0.13, is by priority. Bless you. Then the clue is that about 92% of the ground shipments, okay? And so that's conditional on it being ground, right? A ground shipment. And so that's why it has to follow the ground shipment, right? And so that's the clue. If 92% of ground shipments arrive on time, then that means that 8% or 0.08 arrive late, right? 1 minus 0.92. And then if we take the 85 or 0.85 on time for express, then 0.15 arrive late. And same thing for the priority, 0.98 arrive on time, which means 1 minus that arrives late. Now for the complete tree diagram, I also want to see, it's helpful to have the combinations, right? Ground and on time, ground and late. But also I want to see the probabilities from multiplying down each of the branches, which would be the probability of shipping by ground and it arriving on time is 0.5336, right? Going down the branch, 0.0464, that's the probability of shipping by ground and it arriving late, and so on and so forth. And I did do my check, right? Make sure that these all add to 1. Right? Otherwise, you're missing some probability and you did something wrong. Right? There's a little, if you've had to do some rounding, which we did not have to do in this case, they worked out to nice numbers. And on the final exam, I'll make sure that it works out to nice numbers. And so don't do any rounding because it'll mess it up. Yeah? So now we can use the tree diagram to answer the questions. What is the probability that a package is shipped by express and arrives late? So it has to be shipped by express and arrive late. Well, from here, because you've shown this work, essentially, you're allowed to just write down 0.0435, right? Because you showed it up above. What's the probability that a randomly selected package arrives on time? So that is, we want to ignore whether it was ground, express, or priority, right? In fact, to map it out, on time is the probability of GT plus, so or, right? ET, T, even cuter, pet. Probability of ET. And then finally, the probability of PT. Right? Any one of those would be on time. And so we want to capture all of them. And so from above, I have 0.5336 plus 0.2465 plus 0.1274. which I did not do already. 0.5336 plus 0.2465 plus 0.1274 puts me at 0.9075. Nice. Good. And then finally, given that a package arrived on time, what's the probability that it was shipped by priority? This one I would say is probably easiest to solve with the formula. Right? And so because you have this given here, which I'll take you to the formula sheet, right? The conditional probability in general looks like this. And you want to map. Okay, so let's see here. We want to find the probability that it was shipped by priority. And so it always throws me off when they give the information first and then the probability that we want. So just make sure you're kind of keeping track of what it wants. The probability of shipping priority, which is our P, given that the package arrived on time. So given T. Oh, and you know what? Because we just did this work, I'm going to replace this instead of, I'm going to just write this here. Probability of T. Instead of writing it in words, oops. Instead of writing the probability of on time in words, we do have notation for it, right? And so I should use that. Because now I want the probability of P and T, which I have from my tree diagram, over the probability of T, which I have already solved for, right? And so you don't want to solve it again. And it will be a daisy chain thing, right? Where I make you do some work and then you use that work in the next one, just like this. So I get the probability of P and T is 0.1274. Bless you. You're so close to saying sayonara to this dusty room. 0.1274 over 0.9075. We get 0.1274 divided by that. I get 0.140385674.9. And I wish I had a more exciting one. How about this one? And a gold star for good measure. Because that's it. You did it. We've got a ways until the final exam, of course, because it's on the 17th. Very, very end. I'll send out an announcement once I've posted the practice final, which will be kind of soon-ish. Until then, thank you for all your hard work, and I'll see you at the final exam. Or maybe before then.